Hello everyone. Let's talk about Taylor's formula to the best of our ability here. Taylor's formula is what we're going to talk about. We're going to talk about Taylor's formula, including Taylor's formula for several variables. This is from some of the brilliant work of Ivan S. Sokolnikov from his book Advanced Calculus 1939, pages 293 to 294, where he speaks of functions of one variable. I have all of this on Canvas for my students for the courses that I'm teaching. So they talk about the function f of x, and it's assumed to have a continuous nth derivative throughout a particular closed interval where x is any point of the interval. There's a lot that goes on here, guys. There's a lot of ways you can look at it. We're keeping x as a variable, and then we're working on it. Sokolnikov gives a brilliant and simple proof of Taylor's formula for functions of one variable, f of x. And this is kind of like the start of how that would look if you're doing something like that. So I'll leave this up here. Eventually, I'll probably erase it to give myself a little more room, guys, because there's a lot of room that I'm going to need, I think. But let's see what we can do. X, again, is a variable, and he kind of goes about it in a very interesting way, I guess you could say. He does an integral from a to x, and x can vary, of a function's nth derivative with respect to x dx. The nth derivative of f of x, the nth derivative of f of x integrated with respect to x from a to x, where x can vary. And we will keep integrating. You do this, you're going to keep integrating this quantity. So what you end up getting is when you do the integral, you get to here. You end up getting this. From this. Then you're just going to keep repeatedly integrating. Basically, you take the nth derivative of f of x and integrate this derivative n times and draw some conclusions regarding the lower order derivatives and f of x and f of a, etc. When you keep integrating, when you keep integrating this quantity, you integrate this quantity right here, and then you repeatedly integrate that quantity between the same limits, a and x. Do you start seeing any patterns? I guess is what they're asking you on this. So that's what they're saying here. So you're taking this, you integrate, and you see what happens. Essentially, here's the argument. When you do this, and again, we saw what we got right there. How did that actually happen? Just to be a little more specific about it, you guys. Like I said, I do have this in the notes written out for you in essentially two places. I'm not going to show you everything that's in these two places right now on the board, but you'll have them on Canvas to look at if you wish. I'll probably give you I'm going to give you the simpler proof for Taylor's formula in one variable, and then we're going to expand that to any number of variables. It says several variables. Better way to put it is many variables, or as many variables as you want in n-dimensional space. N-dimensional Euclidean space, we can keep doing this integration. We can figure out what's going on with any n number of variables in Euclidean space to actually find out what's going on. We can expand the Taylor's formula for that in those circumstances. So what's going on? Forgive the repetition on this, guys, but once again, just start it right here, and let's be a little more, I guess you could say, a little more rigorous about the whole thing if you want. You've got the nth derivative, of x with respect to x integrated, and that gives you, this is what we got just now, right above this actually is what we got, and you did it between these two limits, and that's where you're getting that answer right there. The derivative is one order less than it was earlier. That's what happens when you integrate. You get this. So good. I mean, that's great. We got that. let's keep going. Let's go, that all implies, if you were to take the integral of the integral, well, we already found what the first integral was. And we're just going to proceed, and we're going to see how that all plays out. And like I said, in the writing, it's a little bit easier to look at this. So we already found this thing I put the square brackets under. And we do this right here, and you're integrating. You got the integral from a to x of this. Then go dx. Okay, well, let's see where we're going to go here. Hopefully we're going to catch a pattern here. The x varies. The x can vary. It can vary up here as well, actually. And that's important, but after you've done all the work that you need to do, whatever x you want to have, you set that particular x, and it becomes an integral. It becomes, in a sense, an integral from a to b after you set x to a fixed number. But you do that only at the end when you make x a constant. So you look at this and you say, okay, well, let me see what I can do. That's what happens when you do this integral right here. Evaluate it between a and x. And the other guy, this tail end guy, this guy ain't varying because it's the function of a constant number, a. X is varying. X is varying up here. I told you x was varying here and here. It's varying. I get it. It's varying everywhere. Once you lock in a particular a, though, it doesn't vary. F of a, the nth derivative of f at a is a constant, some constant. The n minus 1th derivative of f at a is some constant. The n minus 2 derivative of f at a is some other constant. A is a constant. When you're integrating a constant, there's nothing happening with the constant itself. So in other words, a constant dx, well, what is that? Well, then it's just this. Then this is minus f of a, the n minus 1th derivative, times, let's see how we write that. I kind of wrote it. When you integrate that, you're getting x. Well, what's the evaluation of a constant times x between a and x? Well, it's x minus, it's the n minus 1th derivative of f at a times x minus the n minus 1th derivative of a. The n minus 1th derivative of f at a times x minus the n minus 1 derivative of f at a times a. So it becomes this when you actually do this. When you actually do the integral here, it didn't really do it. Some of the books just kind of assume you're doing this. I noticed that. Let me quickly maybe kind of say it. You're basically getting this. X, and you're evaluating it between x and a. Well, that's an x right here minus, that's an x right here times that. An x put in here times that minus an a put right there times that. So at the end of the day, it's really you're getting the x minus a in here. That's how this business is going to proceed, you guys. So as we look at it, and so on and so forth with this thing. So let's see what we've just done. There's got to be something we can say in regard to it. So we have all here. and we're just proceeding with the same quantities under consideration. How many times are we going to do it? Well, I got the nth derivative there. If I've got the nth derivative, that's n derivatives that have been taken. I'm going to do n integrals to completely not have any derivations going on. I'd like to see what happens. I'd like to ask a few questions. What happens when you repeatedly integrate derivatives? When you repeatedly integrate high-order derivatives, what happens? What's their behavior? But let's be very careful about that. Well, you're repeatedly integrating high-order derivatives, and we'll see how that plays. So we can kind of get a couple looks at it. So, okay, I erased everything there, but it's the same problem that I'm doing, and I'm going to keep integrating it. We've got some arbitrary natural number n. It's the nth derivative of f at x. There's n derivations, there's n derivatives that have taken place. The n derivatives that have taken place, I am going to integrate n times and have no more derivations showing up, I guess you could say. No more derivatives showing up. I keep misusing that terminology. So the n derivatives have been taken. If we do n integrals, we no longer have, in the symbolic sense, in the sense of the variable x, the function of x is somewhere going to appear. The derivatives, they're not gone, they're somehow present, as we'll see, but at least I'm getting to f of x if I do n integrals, because there's n derivatives that were done to get the nth derivative. To get the nth derivative of f, there was n derivatives that were done. So with that in mind, the integral from a to x, so I'm doing two integrals. Well, you saw me do it. I'm using Dr. Sokolnikov's terminology in shorthand, I guess you could say, on this. He's taken this and writing it like this. That's not something you commonly see, but it just means dx dx. You're integrating twice, and the dx is going to be present. There's the d. You're going from the inside. You're going from the inside out. From the inside out, there's a dx on the inside, and there's a dx on the outside. Some of the stuff you'd seen earlier. Well, okay. I mean, we're doing the whole song and dance, guys, and we end up getting this. Pretty interesting stuff. Okay. Right, that's after two integrals. We get to that. So what we have here okay? So we're looking at all this, you guys. Let's proceed. As we proceed with n integrations, we can already sense a pattern developing. And like I said, hopefully we can, like I said, let's get down. Let's do some of the real heavy lifting now, and then later on we don't have to do that as much. We've seen the pattern, and we can kind of work with it from there and see what we can say. So let us proceed, I guess we could say, guys. Let's do three integrals. Well, three integrals aren't that difficult to do if you already did two of them. If you already did two of them, you just integrate the result of those two. You integrate one time the result of those two integrals, and you should be in pretty good shape. So let's write it here kind of like explicitly in symbolic fashion. And when you do this, integral from a to x And we end up getting, again, in my writing here, in my actual hardcover paper, I think the copy got truncated a little bit, but I don't think it will be when you actually see it online on D2L, you guys. So you've got this. Let me try to write this in there. Here's x. It's not the best writing in the world, guys, but it's the n minus 2 derivative of f at x. N minus 2 derivative of f at a. Now, a is a constant once you lock that thing in there. You write it right here. X minus a. Yeah, this looks awfully familiar. We just did this. Yeah, we got that done all over there. Now take this. Two integrals have been done here. Do an integral again, and this is the third integral that's taking place here, you guys. What is that? Well, what it is, let me see exactly. I gotta make sure you feel comfortable with what I'm doing here. When you actually do this, you're going to get, a bunch of stuff here. You're going to get, well, you knock down the order of the derivative. That's what happens when you get an integral done the right way. Let me see here. Here's an a. Here's an x, so that guy was getting integrated that way. The other guy stays. This is kind of interesting. And you got an x minus a right here. Okay, it's a constant. The first guy, when we had done this, we had that constant term, the n minus 1, that stays too. You already had an x minus a. You were integrating the x minus a, between a and x, and that got you this. 1/2. That 1/2, you guys, is the same as 2 factorial. So, all of this and we got that. Okay, let's keep going. That breaks down further. I mean, once you evaluate here, the x goes here, the a goes here, everything else stays the same. Let's do it. Let's write it down, and let's see what kind of a pattern develops. There seems to be a pattern here. Yeah, those constant terms associated with the n minus 1th derivative of f at a, that's a constant. It stays. When you integrate that, nothing happens to the constant term, but you end up picking up an x minus a factor. You ended up picking up a factor which is the quantity x minus a. You integrate that quantity x minus a again, you get the quantity x minus a squared over 2, or over 2 factorial. You integrate the quantity x minus a squared over 2 factorial. If you integrate that, you end up getting the quantity x minus a to the third over 3 factorial. You integrate that, the integral of the quantity x minus a to the third over 3 factorial, the integral of that with respect to x is going to be the quantity x minus a to the fourth over 4 factorial. There's definitely a pattern here. The guy that first showed up is going to get hit multiple times with this integration. The later items that show up as a result of integration don't get hit by as many additional factors, but they do get hit by additional factors. The earliest items that show up have the most factors showing up. This n minus 1th derivative of f at a is going to hit n minus 1 times. N minus 1, there's gonna be the quantity eventually, when you keep doing the integrations, the quantity x minus a to the n minus 1 over the quantity n minus 1 factorial. The ones that are less than that, like the n minus 2 derivative of f at a, it will have an order, the polynomial associated with that will be an order 1 less. So on and so forth. Till you get to the end where hardly anything. There's going to be an f of a and no x minus a. The first derivative of a is going to be x minus a to the 1 over 1 factorial. I guess there's a pattern here. At the end of the day, the order of the derivative that's present is going to tell you a lot about the polynomials that are tacked onto it in a multiplicative fashion. Well, look, let's maybe jump in the gun a little bit here, guys. We got down to here. Look at this guy and then keep working with it. Let's do it. Let's see what happens. Okay, so as this whole thing was playing out, you got all the stuff I erased, it's still alive. This is all one big equation, right? This equals that, equals this, equals that, equals this, equals that. So we're saying all these equal things here. We did it with the third integral. At the end of the day on all that, guys, excuse me here, over 1 factorial, or you can write that a whole bunch of ways actually, guys. Okay, I mean, this is the same stuff I was just talking about. Not cleaned up incredibly meticulously, or not cleaned up to the point of, wow, it looks a lot different. Yeah, it should look a lot similar to what I wrote earlier is I guess what I'm trying to say, guys. We cleaned it up a little bit. We actually did the evaluation here and got to there. But look at this. There seems to be a pattern here. I got the quantity x minus a to the 1, the quantity x minus a to the 1 over 1 factorial, the quantity x minus a to the 2 over 2 factorial. I got a feeling as we do n integrals, we are going to get everything not to the nth power, because this was after 3 integrals. After 3 integrals, we got it to the second power. After n integrals, we're going to get it 1 less, just like 2. Just like 2 right here is 1 less than the 3 for the 3 integrals we did. It's going to be 1 less. It's going to be the quantity n minus 1. It's going to be quantity x minus a to the n minus 1 power over the quantity n minus 1 factorial times the n minus 1th derivative of a, period. So this guy's really going to get a lot of action to the point where it gets, if you keep doing integrals, to the point where this 2 is going to be the quantity n minus 1, and this right here is going to be the quantity n minus 1 factorial when it's associated with it, when all is said and done. This one right here is going to be the quantity n minus 2 over the quantity n minus 2 factorial because it's associated with the n minus 2 derivative. Okay, there's a pattern here. The first derivative is going to have it to the 1 power, the x minus 1 to the 1 power over 1 factorial. And the f of a, no derivative, is not going to have anything there. So this is the pattern that is going to emerge if you do n integrals. If you do n old school integrals on this thing, what's going to happen? So, you've got to observe the patterns and see what's going on here. But this, I'm already kind of spelling it out where it's going, you guys. If you take all of this, let's see. Basically, let me kind of argue how I want to do this. If you take that whole thing right here, that was after 3 integrals, ladies and gentlemen. Do a total of 4 integrals. Do 1 more integral, and that'll be if you're doing the 4th integral on this. And that's the same as, hey, you started right here. You started here, plain and simple, and then somebody said to you, well, here you go, I just gave you this. Do something here. Do n integrals. I'll tell you what I'm going to do. Let me do 4 of them first, and we'll take it from there. Do 4 integrals there. You can write this a lot of ways. I'm not a great fan of this notation that Dr. Sokolnikov is using, but it's fine. The repeated integral is good to have them away from each other, I think, but that's kind of an unwieldy process in many regards. When you actually do it, what's going to happen? What's going to happen is what is right here. That's a constant. Do the integral here. That's going to be to the 3rd. A 3 is going to be on the bottom. Well, 3 times 2 factorial is 3 factorial. This is going to be a 2. 2 on the bottom here. 2 times 1 factorial is 2 factorial. You get the picture. This one's going to get hit, and it's just going to be x minus a when you do it. This one right here is going to be f, the n minus 3 derivative of x, minus f, the n minus, this is going to be f, the n minus 4 derivative at x. So the n minus 4th derivative of f at x minus the n minus 4th derivative of f at a. This is where it's going to happen, and all this other stuff, these guys are constant. Yeah, they're constant, but these guys are not. So, and the integral is going to be taking place like that. So when you look at it, the whole thing goes, stuff's easier done, I guess, when you're doing it on your own, pencil and paper. You can kind of catch the subtlety of what's happening because you're actually working it in real time. Now, I do have it written out for you on paper, so you can always look at it and take a shot at it on your own if you wish to go there. What's going on here? Well, that happened. We did the integral, and you had the n minus 4. The integral of this is n minus 4 derivative of f at x minus the n minus 4 derivative of f at a, because you're integrating from here to here. So this got you this. Everybody else has an association with a constant in front, And the only integrals that you're doing here are integrals of polynomials. Here you're going to tack something onto this guy. So what happens is, it's a little, you know, it's obvious. I'm not going to say it's not a little confusing with it. You got that. Well, this guy, like I said, the first item that came into play that was a constant is repeatedly getting hit. And it will until the end of the whole thing. He's going to have the biggest order polynomial associated with him at the very end. And there you go. That's after 4 of those. Guess there's a pattern. Whatever, you're doing 4 integrals. You know, and it's knocking down, you know, like I said, it's the n minus 4th, the 4 integrals, it's n minus 4, n minus 4 present, n minus 3 present, n minus 2 present, n minus 1 present. 4, 3, 2, 1, that's 4 integrals. It goes from n minus 4 to n minus 1. The first integral that got done didn't really associate a big polynomial. But afterwards, the polynomial x minus a to some power started manifesting itself after the first integral. So there's going to be n minus 1. There's going to be the highest order polynomial is going to be n minus 1 after the n integrations. And that's n minus 1 polynomial is going to be here when you're done integrating this thing. It's going to be n minus 1 to the n minus 1 power to the n minus 1 power to the n minus 1 to the quantity n minus 1 factorial underneath, et cetera, et cetera. This is going to be x minus a to the n minus 2 power over the quantity n minus 2 factorial. Okay, so they're all lining up together. At the end of the day, they're all going to line up together. There's going to be a point where it's going to be n minus n, which is 0, which means there's no derivative taking place. And that's just going to be f of a. That's going to be f of x and f of a. That's it. Let us observe the patterns which are seen and apply them to all n integrations. So when you finally do it, guys, let's write it down for you, and we'll kind of figure what we want to say pertaining to it. There's a number of ways I want to kind of look at them. I'm going a little bit against my notes a little bit later, I think, when I do some of this stuff. But let's see what we can say. Okay, so you see what we got the pattern here, guys. And let me just kind of say what I've been trying to say within the last couple iterations as to what's going to be happening here. How's it going to look? All right, guys. Let's, without further ado, let's kind of look at it, draw some conclusions, and talk a little bit, and see what we can say. If you're going to integrate repeatedly, and we've been saying this quite a bit within the context of our discussion thus far today, if you're going to integrate n times the nth derivative of f at x, if you're going to integrate the nth derivative of f at x n times, like this, where x is a variable, it is going to play out that we're going to get, it's a lot we can say. So let's just, at the end of the day, you guys, it's going to come out here. But that's the argument. That's the essential argument as to what's happening. This is the first derivative of A. They usually put a prime, when they do it. I'm not doing that now. The one looks good when it's associated with that one too. Maybe the aesthetics are a little easier that way. Okay, something I did. All right, guys, it's basically the argument I was talking about. Those factorials are pretty important. They occur in a lot of places. When you're trying to derive what that great number, very useful number, very fascinating number, E is, the derivation of E involves factorials, involves combinatorics, and it gives you that interesting conclusion as to what E is. E is 1 plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial, plus ... on into infinity. And that actually converges. You can prove that it converges. You can get an approximation to any degree that you want. And you can do a lot with that infinite series. And you can do all sorts of things to derive what goes on when you exponentiate that series, e to the x. You can even put it with complex numbers. Any real number, any complex number, you can make it make sense. And you can derive a lot of fascinating things with it. And the combinatorics that take place and the factorial notation and knowing what factorials are plays a big role in being able to do that. That's not what we're doing here, but there's something to it. Okay? This has got far-reaching applications, the factorial notation does. That's for sure. Okay, so well, I mean, I was trying to give everybody heads up as to what's going on with this. You're seeing it. How many integrals are you doing? Well, I don't know. N could be a pretty big number. N could be as big a number as you want it to be. It could be as big a natural number. N could be as big a natural number as you want it to be. That's for sure. So let me just see here, guys, what I want to do. Well, what I want to do is not write this down incorrectly as I did right now. That's a minus. That's a minus. There's going to be pluses later on. We'll start crossing all those bridges as we need to cross them. So here's dot, dot, dot as we're going across here, guys. So let's see here. We got this. We subtracted here. We got the dot, dot, dot business. We got it goes. I guess we just kind of quickly let it go to here. I mean, the factorial notation is everywhere. It has some really far-reaching applications, you guys, that's for sure. When we talk about determinants, we can look at factorials to kind of help us count how many terms are present when we're talking about determinants, and they have their own great usefulness. Kramer's rule, for example, right? So again, factorials are there, and some wonderful applications associated with them, that's for sure. Here's one of those wonderful applications. We're here. Let me stop right there. I mean, that's what it is. That's what that integral is, actually, you guys. We took this guy right here. You did the integral. Then you got all this. Well, I don't know. Can we kind of figure something out here? Can we kind of figure something out. Yeah, well, that's a lot to figure out right there. There's a lot here. I'll tell you what I'm going to do. What do you say we get f of x? What do you say we get f of x all by itself, and we take all these items, which are all subtracted from f of x. Why don't we add the opposite of the, well, you know, these are items, this is all subtraction. This is all subtraction to the right of f of x. Why don't you add, you're minusing f of a, why don't you add f of a on each side? You're minusing the first derivative of f, add a, why don't you add the first derivative of f? Why don't you add the first derivative of f, add a, times the quantity x minus a to the 1 over 1 factorial, etc. Basically, why don't you take all of these subtractions and add, which is the same as plus a negative, plus a negative, plus a negative, plus a negative. Why don't you add the opposite of these negatives on each side? Or simply, why don't you just add, you know, get all of this stuff here, guys. Do the algebra. Do the algebra, get all of this stuff over to that side where this guy is. What do you got then? Well, when you do that, okay, again, everybody sees what I'm saying here. You could make this minus f of a minus this, you know, this minus that, minus this other thing, minus yet another thing, minus yet another thing, minus, minus, minus. All right, take all those minuses, add the quantity that was being subtracted, add that on each side, and then you just get this guy all by himself. If this guy is all by himself, add those on each side. You're adding it onto him. What you end up getting is this. Let me write it down. So you're adding all these up to this guy. So what does that mean? Well, it means plus and what happens, well, let's make the long story short, I guess you could say. Let me see here, guys. All right, guys. Basically, maybe I'm talking myself in circles here, confusing you more than I'm going to help you, and that's certainly not my goal. Forgive me if I'm doing that. Basically, I'm just saying, just do the algebra on that last. Do the algebra on that last equation and solve for f of x. Period. Do the algebra on that last equation and solve for f of x, and you got this. It's as simple as that. That's f of x. F of x equals f of a plus the first derivative of f at a times the quantity x minus a to the 1 over 1 factorial, plus the second derivative of f at a times the quantity x minus a squared over 2 factorial, plus the third derivative of f at a times the quantity x minus a to the third power over 3 factorial, plus dot, 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 plus the n minus 1th derivative of a. I told you he was going to get hit a lot. Plus the n minus 1th derivative of a times the quantity x minus a to the n minus 1 power over the quantity n minus 1 factorial, plus the integration done repeatedly 5 times of the quantity, the nth derivative of f of x, This all arose from that last integral. Remember when I did that whole integral? We looked at the whole integral. What can I do? Well, I got the whole integral equal to that whole mess. Let me solve for f of x by adding all the opposites of plus the negative that was over there. Subtraction is the same as plus the negative. In short, solve for f of x, you guys, and you get to here. Well, that's Taylor's formula. That's Taylor's formula for one variable. And that's great. So, that's great, but I'd like to know, I mean, it's telling me a lot, and yet there's a lot I'd like to know. This tells me a lot. The problem is, yeah, okay, great. I mean, I guess I can approximate that. If you want to talk about a particular x, do all the mathematics here on the right-hand side, and you'll get a good approximation. How good's your approximation? It hinges on this remainder right here. This guy right here is the remainder. This integration taking place n times of the nth derivative of f at x. This integration taking place n times of the nth derivative of f at x. That integration, wow, I guess I'd like to know what that is, because I can tell you the exact answer. If I don't know the exact answer, can I at least get an approximation of what that is? Can I put some boundaries on where that thing is? Yeah, you can. What's going to happen is, well, I mean, I'm trying to save some time because the writing this stuff takes kind of forever. I wrote that right there. Let's talk. Let me kind of tell you something, and then more rigorously tell you the same thing. Hopefully in a more rigorous manner when we talk about it. Just trying to argue with myself where to go with this thing when I'm saying it. I'd like to know what that thing is. Okay, at least some approximation. Well, they make the claim there's an argument you can make. And here's the argument. You can take just trying to argue now with myself where I want to take this, because I don't very much like, oh yeah, okay, that's okay, yeah. All right, if you took the integral from a to x, and you're going to do that n times onto this, on this function. Now, we already talked about this. I erased it. I know, I get it. I erased it, but let's talk about it again. We're talking about this right here. dx to the n. In my notes, I forgot to put the n this particular one time when I was writing it down. Not a big deal because we're going to do something now. But let me talk to you. Guys, I think we can get out of the woods here. Well, at least they claim we can get out of the woods, and I'm going to prove to you later it's actually valid. Perhaps the proof itself is, I don't know, perhaps it's going to be unnecessary when I do it, but to me, I think it makes a lot of intuitive sense. So I'm going to go there. Let me show you the way this is frequently argued. And then let me show you a way that I don't remember it being frequently argued a lot, but I'm sure I'm probably wrong. I'm sure they probably do this in some, in different places it gets done. Maybe I just didn't pay attention when they had done it. But this is one thing I have seen, and then I'd like to do something that I think is more intuitive, more rigorous. But let's before we get more rigorous, can you say this much with me, guys? That you could write it as the integral from a to x doing all these, right? I mean, and, okay, we want to be extremely careful how we do this. I'm not thrilled by the way I wrote it myself, to be honest with you. So I'm sort of debating with myself what I need to do here. But I'm going to leave it like that. It's a little different. I'm going to write it a little differently than how I wrote it. Write that here. I'm going to take this guy right here. And these guys right here are n minus 1. And this is 1, which is n. These are n minus 1 of these guys, and this is one of them. N minus 1 and 1 is n integrals. Here's one integral, and here's the remaining an indication of the remaining n minus 1 integrals. I'd like to take a look at this guy right here. Well, by the mean value theorem, you can find that this guy right here is going to be the nth derivative of f and some number xi, the Greek letter xi. The nth derivative of f at x integrated dx is going to be, by the mean value theorem, the nth derivative of f at xi, where xi is between a and x, multiplied by x minus a. Yeah, that's fine. Now, this is a constant, ladies and gentlemen. That becomes a constant. This varies. If you do n integrals, remember I did one of the n integrals, so these are n minus 1 integrals right here. N minus 1 integrals right there. If you repeatedly integrate this thing, remember this is a constant, ladies and gentlemen. You get the nth derivative of f xi, x minus a to the n over n factorial. Okay, interesting. Okay, so yeah, and they write this, and like I said, it gets written in different. You can write it in different ways. In my notes I write it slightly different. What's that mean? We just did it. We just did it. I'll be honest with you, I've never been thrilled with what we just did. I think there's more of an argument for it to kind of really give the motivation as to why that's true. Remember, it's true, guys. You guys got the reverse feature on this whole thing. But really, so this is the claim we're making. So you're telling me that, well, yeah, that we just did it. Way over there, top left-hand side, way over there, top left-hand side is this, and this right here is equal to that. Well, this gives you an idea of how, even if you can't get the exact value, you can get an idea of what the error measurement is on this thing. And that's to the n over n factorial. When you do it, pretty remarkable. Yeah, that's true. Yeah, okay, that'll do it. Fascinating conclusion. I'd like to look at it a little differently. I mean, this is good. This is true. End of the story. It's true. It's Taylor's formula. The way it gets written a lot of times, they'll put these guys, the quantity x minus a squared over 2 factorial, they'll put it in front of the f when they write it. And in my notes, when you look at my notes, you see that I simply, by the commutative property, just switch these up. By the commutative property, we switch these up. By the commutative property, we switch these up, and so on and so forth. That's not a big deal. But that's, that's actually how it works. That's Taylor's formula for a single variable. Okay. We're eventually going to go to Taylor's formula expanded for n variables. We'll see how it plays out. We'll see how much time we got when we actually try to run it, but I think it's an important thing to be able to do. I leave this, it's as it is. Again, the way I have it in my notes, I've got this factor in front of this. Likewise, I have this factor in front of that. Likewise, that factor in front of this, etc. Not a big deal. Just the notation. So just look what's going on there. Yeah, it's nice. It comes out nice. And we do get this for an answer. But whatever. Yeah, I mean, it's true. It's a true statement. But what I'd like to say is, I'd like to look at it a little more rigorously, to be honest with you. I just want to look at this part more rigorously. So let me get rid of this stuff. You guys have it. You know what it is. We're not worried about the aesthetics that much. We know that if you put this in front of that and this in front of that and so on and so on, it's the same thing. All right. So we did this. I'm dying to know. I'm dying to verify that this guy is the way it is. We're really like to see that that's actually true. This is from the mean value theorem applied onto the function, the nth derivative of f. So whatever the value is that's going to make this thing kind of the mean value so that you can multiply it. So you can multiply it by x minus a over here. That's what you did initially. Guys, you multiply by x minus a regarding the nth derivative of f. The nth derivative of f with respect to some variable x. The nth derivative of f with respect to some variable x, and you did it, and you worked it. For the nth derivative of f with respect to the variable x, there's a psi that if you multiply it by the length of the interval's from a to x, so x minus a is the length of the interval. Length of this interval times the mean value of the nth derivative of f within that interval from a to x. And I said we multiplied it by the length of that interval. That'll give you the first integral. Then you just kept doing integration. This guy's not changing. It's a constant. This is what's varying. Repeatedly integrate this thing n minus 1 times. Believe it or not, yeah, it's as it is, because remember now, this is already one integration to get this, in a sense. N minus 1 time, that's where you're getting this. Wow, that's pretty convenient, I guess you could say. Let's see what's going on. I'd like to see another way to look at it. It is going to be this answer. So let's see. What's going on here? Well, again, it's in the other, it's in another discussion. It's in another packet on Canvas that I have this. Considering Sokolokov's brilliant work again. We said a number of things there. Let me try to maybe hit the highlight to just get to it. You know, again, the question is, I want to, I guess, keep asking the question until I answer it, I guess. You could call that integral from a to x dot 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 of the nth derivative of f, the nth derivative of f in regard to the x variable, so if you do n integrations if you do n integrals, you're going to get something. We talked about it. We drew a conclusion. I still got some questions. So let's see what we're going to say here, guys. So for this right here, they gave it a name, called it R sub n. The remainder associated with n integrations. Some sort of remainder, what is equal to, the whole thing. We already did the song and dance, you guys, and we drew the conclusion. Now, let me now put this in front, I guess. It's the same conclusion you drew earlier, guys. It's the same conclusion we all drew earlier. Yeah, that's the conclusion we drew, and I'm still asking you why. Yeah, I know why. We did the mean value theorem on the first integral. We got the nth derivative of f. We did the mean value theorem on the first integral, and we got the nth derivative of f, xi, the nth derivative of f xi times the length of the interval. That's the first integral. That was at the first integral. True. Do n minus 1 more integrals. This is constant, this varies, you get this. I get all that. I get all that. In fact, I even believe all that. But I believed it more after after I did something else, I think, that I want to kind of show you. Okay, so we know that. They're calling it R sub n. That's just the remainder. They call it, that's that last integral that was showing up. That last thing that tells us how far off is that thing if we were just to truncate it. How far off is our approximation using Taylor's formula if we do that? Yeah, that's great. We did it. We got to here. I get it. But why is this so? I will attempt to explain this on film and or in person because that is likely the most efficient way to proceed. But for now, please consider the following. Okay. Well, it turns out I kind of kept my word to myself. I'm trying to do this on film, so let's try to do it. My take on this is the following. Tell you what, that nth derivative of f definitely has a minimum value, probably, may not, but maybe all the values are the same. So the minimum value is the same as the maximum value because it's a constant. But let's look away from maybe trivial examples and say, all right, there's a minimum value there. Nobody's smaller than that minimum value. No value is smaller than that minimum value. No nth derivative of f is smaller in that interval than this particular minimum that I'm claiming. And no value of the nth derivative of f is greater than this maximum value of the nth derivative of f that I'm claiming for that same interval between a and x. So what's going on? Well, tell you what I'm going to do. We say it comes out to here. That's the claim we're making. Let's kind of prove it. Tell you what. Let's take this and say indeed that's n integrations. It's a lot more subtle than this, guys, because you're here's where I was having issues. Maybe you're having them too. We're not going to lose a whole lot of sleep on it, but maybe this is a function. And once you integrate from a to x, x itself is a variable and it can change. And you're integrating along that path. And basically every single integral you got, you can put it number of ways we can kind of look at it. Let me try to see how I want to say this. Every integral that you integrate this, but there's a lot of there's an infinite number of integrals you could have here, depending what your x value is. X goes from a all the way to some x, to some b. But that x varies when you're doing the integration, but also it becomes a limit of integration. So even once you do that integral, there's still the function associated with x happening. I'm sure I'm not saying this in the best way. Let me just kind of say there's much more to this than meets the eye. It's not just, oh, you do this, it's done. Not really, because there are very many integrals that are very many infinite number of integrals that can be taking place, and each one of them tells you each one of those integrals is a value of a function that you're going to be integrating again when you do the second integral. And then when you do the third integral, it's the same thing over and over. So it's not, to me, it was never that obvious. Perhaps it is, and I'm simply missing something. But this is why I want to say this. I'll tell you what. If that's true, the integral from a to x, okay, here we go, n of them, right? Let me take the minimum of this guy. Let's not worry about formalities that much. We ain't worried about the formalities, guys. We're going to say there is the nth derivative of f. The nth derivative of f at x, there is somewhere a minimum value for that function. That function, the nth derivative of f at x, there is a minimum value. Minimum, huh? If it's minimum, it's a constant. It's some constant minimum. So I'm going to integrate. Okay. That's the argument. You're going to see what I'm doing in a second. I'm going to integrate n times, guys. It's the same kind of business that happened over here. It's going to be x minus a to the n over n factorial. It doesn't matter if I have this on the back end of this or on the front end of this. It doesn't matter. If it's in front or in back, it doesn't matter the way this is working out, guys. And it's what? The nth derivative of x min. Yeah, that's true. That's what it is. That's what it is. Okay. We took all this, and we got this. All of this. Yeah, okay. Good enough for me right now. Now what? Minimum value possible for the multiple integration because the nth derivative of f at x minimum is the minimum possible value. This guy right here, the nth derivative of f at x min, the nth derivative of f associated with the x variable over the interval a to x min, the nth derivative of x, the nth derivative of f associated with the x variable, its min over that interval is the minimum possible value of the nth derivative of f at x for a particular interval of the domain. Likewise, we're going to do it for the max, you guys. We're going to do the same business for the max. We're going to take the integral from a to x. You know where I'm going now. The integral from a to x. Now I'm going to find a big value, the biggest value I can find associated with that interval and associated with that function. The function, the nth derivative of x, the nth derivative of f at x. Try saying that 4 times quickly, right? You got this. Guys, it's the same argument. Please don't let this surprise you. I mean, this is a constant. That's a constant. Do the multiple integration. It's doing a lot of the same business we already did. What happened? Let me think about. Yeah, right. It's the same thing. You can go over and integrals. That's max. That's the max. So what's going on here? Here's the max. What did we just discover? We discovered the integral's got to be between the two. The real integral's got to be between the min and the max. So the maximum possible value that will or could occur, better stated, for the multiple integration, this is the minimum possible value. This is the minimum possible value that could occur for the multiple integration outlined here that we've been doing all along. This is the minimum possible value in that interval that could occur, the interval from a to x. This is the maximum possible value that could occur. It's the same thing, it's the same look to it. This one's just sub-max. This one's got a max underneath it, and this one's got a min underneath it. Replace the min by a max, you got the maximum value that's going to occur. So what's going on here? What's going on here is pretty basic. Let's take a look at the min. The nth derivative of x, whatever that is. Let's get that min value. And that's going to be less than or equal to r sub n. Is going to be less than or equal to, r sub n was just that integral, that multiple integration taking place. Nth derivative of f at x. Here's the max, guys. That's all I wrote here. I don't know how good the film's going to show it here, so it's right here. The r sub n is just that multiple integration. The r sub n is just that multiple integration. So that's the r sub n, the multiple integration, which just means this. Sorry guys, I bunched it up, I guess. But that's just that multiple integration that we've been doing all that time. And there they are. So, write that a little bit better, guys, so you can see it. I know you know what it is, but let me just. That's huge. That's of significance. I mean, I think. You kind of this is huge. Yeah, I mean that's a big thing right there, guys. So we did that song and dance, so we can kind of say something here when it comes right down to it. I'll show you a number of ways to look at it. Let me stay rigorous with this thing. It's going to take a little bit longer, guys, but I think it's worth it. Let me stay what I think is a pretty rigorous way to look at this thing. Okay, what's going on here? Well, I'll tell you what, I mean, the quantity x minus a to the n over n factorial is the same as the quantity x minus a to the n over n factorial. Again, we got this here. So, I mean, we got this quantity, the quantity x minus a to the n over n factorial is the same as this quantity over here, the quantity x minus a to the n over n factorial. Why don't you divide all the way across this inequality by this quantity right here? It's going to be saying, the worst that can happen is if you're dividing by a negative number, depending upon the exponentiation taking place, if it's an odd exponent, if n is an odd exponent and x minus a is a negative number, an odd exponent, take a negative number and exponentiate it to an odd power. Take a negative number and exponentiate it to an odd power. The negative, it's still negative. A negative number taken to an odd power is negative. So if you divide by that quantity inside, these guys end up flipping around. Yeah, they do, but the goalposts don't change. That guy's stuck in the middle of it. That's the big thing. That's the big consideration. For our purposes, we're not worried about that. We're going to say x is bigger than a. If x is bigger than a, if x is bigger than a, x minus a is a positive number, and then there's no issue there. I'm going to leave it like that. All right, take this divide by this all the way across on each side. So you end up getting the nth derivative of f min less than or equal to. Sorry I write so huge, guys. I just want to make sure you can read what I'm writing. The nth derivative of x okay, it's still sandwiched between there. Okay. True. Yeah, true. I hate to run in circles with you on this. Where am I going? You're thinking, where is he going with this thing? Well, I'm going a lot of places. Going a lot of places here. What we're going to say is, that's a complicated looking thing. It's not going to be as complicated we kind of figure how I want to say this in a sense. This is all true. Let me do something to it, I guess. Okay, we got what we got. Where do you want to go with this? Now let's leave it be. Leave it be for now. Do you mind if I were to say this guy right here equals something? Yeah, okay. I certainly didn't say anything too profound when I just said that. I certainly did not say anything too profound when I just said, hey, it's got to equal something. I agree. Yeah, not only does it got to equal something, it's got to equal something that's between the minimum value and the maximum value. And because the function is continuous, there is a value of psi such that the nth derivative of f at psi is a number that is between these two. Remember, these are continuous functions that we're working with. What does that mean? There's no holes in the graph. There's no holes in the function. These are continuous functions with which we are working. These are continuous functions with which we are working, you guys. Is there a number between the nth derivative of f at x in the interval from a to x that's a minimum? Is there a number that is between nth derivative of f min and nth derivative of f max? Yeah, there's a number between it. In fact, this number is one of those numbers that's between it. Because the function, the nth derivative of f, is continuous, all real number values will be hit that are between the real number values of nth derivative of f min and nth derivative of f max. There is a value psi in the interval from a to x. There's a number psi somewhere inside of the interval from a to x. There is a psi such that the nth derivative of f at psi is between these two and is equal to that. That's huge. That's huge when you look at it. I mean, and we're saying, if I divide, there is something between it, and this guy right there has got to be. And I showed it a little differently in the in the work that I put on Canvas for you. A little bit different, but it's the same kind of argument. Oh, so there is a number between there, huh? Yeah, there is. Now because of again, I'll say it again. Now because of the continuity of the function, the nth derivative of f associated with the x variable, now because of the continuity of the function, the nth derivative of f of x, throughout the interval of consideration, all real number values, ladies and gentlemen, between the nth derivative of f min and the nth derivative of f max, all real number values between those are attained. So there exists a psi such that you want to put the max over there and the min over here? Who cares? That's not a big deal. The big deal is that all real number values are attained between the max and the min. Really. If they're attained, this song and dance right here can be gotten. Absolutely. That right there and this right here are identical. Somewhere. I don't know, there's a value somewhere. I did not say I knew what it was. I just know if there is a real number, equal to this mess, if there is a real number equal to this integration taking place n times, and then dividing the result of that integration taking place n times by the quantity x minus a to the n over n factorial, and that all of that answer is between the max value of the nth derivative of f and the min value of the nth derivative of f. If it's between the two of those, all real numbers are attained between the min and the max of that continuous function, the nth derivative of f. If all real numbers that are between, in other words, if this was 2 and this was 10, all real numbers, including the number pi, including the square root of 7, including the square root of 10, whatever, all real numbers are attained somewhere. The function, the nth derivative of f, will span, will attain all the real number values that are to be found between the nth derivative of f min value and the nth derivative of f max value. That's really important. All of the, whatever's between there, man, if there's a number between there, the function hits it. The function is doing this. Here's the min value. Here's the max value. Build a number line here. There's no, go here, put a number line here. Everything on the number line is there somewhere. I can find it. The function's going to hit something on there, either here or here or here or there or there or there or there. You name it. Okay? That's all they're saying for that. So all values are attained. Here's the min of the function, the nth derivative of f. Here's the max of the nth derivative of f. And this is a quantity. And for a given value, for given values at the end, for given values of a and x, this is a set quantity. It's something. If it's something, its values between the max and the min, and it is attained by the nth derivative of f function somewhere. There it is. Now, it could be a psi that's the same. It could be a psi that's different. We don't, that's another issue here, but maybe it isn't. And again, I talked about it in a number of ways. I don't know. I think hopefully what I've said now is enough to kind of get you there. But if that guy's this, are you telling me that this guy right here times just ran out of room a little bit, guys. That's the only problem here a little bit. So if you're going to multiply again by x minus a to the nth over n factorial, this guy, and you're going to do the same thing here, x minus a over n, x minus a to the n power over n factorial times this guy, and that's the max that we talked about. And then we could do the same thing here, but let me not write the min here, try to buy some room here, guys. And this is x minus a, and of course my chalk's starting to puke. All right, so let's, yeah, there's the n factorials here. This guy we just said, that guy we just said, we did the whole song and dance here. Let me erase it. That guy, you know, this right here was equal to the nth derivative of f xi right there. I was trying to buy all this room. Now I got all this room. But there it is. Well, wait a minute. Now you might want to say to me, yeah, okay, Malus, that's fine. Not so fast. How do you know this psi is the same as that psi? For right now, why don't you just call this guy psi sub 1. Call him psi sub 1 for now. We don't know. Yeah, no. Let me tell you something. Psi sub 1 is equal to psi. Why is that? Because this guy makes it work. And the integral, the multiple integral for at the end, when you set the values of x that you want, real numbers x, now you're not using variable. Initially you're using x as a variable. Once you set it to something you want, once you've set it into a particular place, once after all that integration's done, once you set this to a particular place, you say, okay, he got the value he got. Let me evaluate the function. This whole thing is a big function of x. If you put in a value of x, bam, it's already there. Then it's like, okay, that was it. If you put in a function of x, that's a definite limit that I was going to. I was going from a to b, where to a to some value of x that I'll call b. Then it's set. This is a unique number, ladies and gentlemen. This is also a unique number. All of this is a unique number. Well, this x minus a to the n over n factorial is the same as, right, look at it. This right here, to give you a look at it, I mean, this basically we're saying they're equal. Psi to the 1 is equal to psi. I just said that. Now, the quantity x minus a to the n over n factorial and the quantity x minus a to the n over n factorial are the same thing. And if this has to be a unique number, once you set a value of x at the very end of all this big integration, at the very end of this multiple integration that's taking place, at the very end of this repeated integration, at the end of these n integrals taking place, when you set a value of x, this is a real number, it is a unique real number, and it's equal to this. Right? And it's equal to this. I agree. This same guy we said is equal to this guy, sub 1 times this. Well, wait a minute. If they're both equal, the integral is the integral. I guess what we're trying to say, and I don't want to erase any of it, is what I don't want to do. But what are we saying here? Well, I'll kind of make it, kind of spell it out, I guess you could say. I think you guys already knew this. I probably got you there about 10 minutes ago, I hope. But let's, to that place, but that how we do this. But you go to here, and we're saying the nth all right, we've done this. Okay, we've ad nauseum we've done that. We discovered, or we claimed that we discovered this a while ago. And I think we're a little more sure that we discovered, this. Yeah, these are unique values though. Once you've done the n integrations, once you've done the n integrations and chose a value of x for that n, you've done the n integrations and you developed a function of x, and you plug in x, it's a unique value. It's one and only one value. It's equal to this. And I'm also saying it's equal to this. Well, that's great. That right there, all of that and all of that are equal. That means this and this got to be equal. If psi and psi1 are not the same, f of psi and f of psi1 definitely are the same. And that's the most important aspect of it. And for sure they are the same as well, because it'll work when they're the same. And that solves it. When we say this, we're getting here. We're getting here and we're getting to this. Definitely, the nth derivative of f xi is equal to the nth derivative of f xi1. And since it's the same function, you can plug this guy into here or that guy into here, and they'll give you the same answer. The most important thing is the functional values are the same. So that formula for the remainder is the same, is true. And that's very important. And there's other proofs. And I have other proofs of how to actually do Taylor's formula. I thought the way that Dr. Sokolnikov showed us initially, and the way I showed it, copying Dr. Sokolnikov, that's the best. To me, that's the best way to do it. All right. I'd like to try to expand Taylor's formula for n variables. I will do that right after. I'm just going to erase this, and I'll come right back and we'll do it. Okay? All right. Thank you. All right, everyone. Thank you for all your time throughout all of this process. Let's talk very briefly, just to save a little bit of time here, because this particular part of the discussion does not lend itself to a brief discussion. So given some of the time considerations that we have, let me tell you, basically we're talking about Taylor's formula expanded for n variables. And I am going to have, those of you who have me as a teacher right now know that I have this on Canvas. Finding it is not really difficult. It's associated with the Taylor's formula discussion that I talked about in a single variable, and then and then some pages in from there, I go into quite a bit of depth in regarding Taylor's formula expanded for n variables. So I'm going to have this gentleman who's helped me out quite a bit with all this whole process, doing some great work, is going to have this, I guess, moving through YouTube for you, so you can kind of look at it, look at some of the people I'm quoting and stuff, and how it gets done. Basically, for n variables, any n variables, no matter how many there could be 1 million variables involved. Well, then you're in, or 5 million variables, then you're in 5 million dimensional space, 5 million dimensional Euclidean space. So in any n variables, you're in n-dimensional Euclidean space. If you build an n-dimensional box, you start from one point that you know the answer to, and you draw a diagonal in that n-dimensional box to the point where you want to actually get an answer. What you do is you take all of those n variables and you parameterize them. You make each one of them a function of t, and t can be from 0 to infinity. For our purposes, we're going to make t go from 0 to 1. 0 where you started, and 1 for the endpoint for where you're trying to get what the answer is to the function using Taylor's formula. Once you make every single variable of the n variables, once you make them a function of t, you have parameterized all the variables as a function of t. Each variable is a function of t. The entire function becomes a function of t, and you're basically doing Taylor's formula as a function of t. You're doing Taylor's formula for n variables as a function of just one variable, a function of t. You're taking Taylor's formula in n variables, no matter how many there are, and if you parameterize each one of those n variables, make them a function of t, the entire function of n variables, the entire function of n independent variables becomes a function of t, just of t. It's a function of a single variable. Then you just do Taylor's formula the way I've taught you how to do Taylor's formula, the way other people have taught you how to do Taylor's formula. You do Taylor's formula at that point in a single variable. Now, you use the chain rule to actually find out what's going on. So each one of those variables, you're still going to take the derivative of the function with respect to t, but to do that, it's a derivative with respect to t, which is equal to a derivative with respect to x sub I times a derivative with respect to, times the derivative of that function with respect to t. And you do it in a whole bunch of different ways. What happens is df dt, d squared f dt, df dt, d squared f dt looks something like this. D mth derivative of f, the mth derivative of f with respect to t, looking something like this, and you got n to the m terms associated with this. So this gets really, it's not anywhere near, once you expand this, and when you make it a single function, a function of t, it's quite easy. Sure, it's quite easy. You do it just like you do Taylor's formula as a function of a single variable. But then once you actually, that's really what it is, but you have to take into account all the variables that are present. And when you do that, that becomes quite the process. This first derivative, you're doing each one of the variables, and then you're multiplying it by the chain rule by the derivative with respect to t associated with the variable. There's n terms here. When you take the second derivative of the function, the process will give you n squared terms. When you take the mth derivative with respect to t, the process will give you n to the m terms here. So it's quite, where where the f is equal to this, and you've parameterized it. Well, it turns out conveniently that it looks a lot like, if you take the differential operators, they exponentiate in a sense. They behave as though they're being exponentiated. The way the operations take place allow us to view differential operators and differentiation to be regarded as the operations are taking, the operations themselves, the operators themselves rather, are being exponentiated in a sense. Not the end result, and in some cases, results are also flat out being exponentiated, but the differential operations are being exponentiated. So if I say to you, perfect example, it's like me saying to you, the derivative, d dt, don't worry about the f, d dt, if you square that differential operator, it becomes d squared dt squared. It doesn't mean you squared df dt, though it can also, though in another place, you actually could be doing just that, but it's not the same as squaring the operator itself. Well, in all cases, guys, there's this analogy that goes on across the board. Pretty beautiful, and very convenient. And it behaves in such a way that if you want to find, assuming you took this to infinity, as far as you want to take it to a very far, very large number of terms, the value of the function, capital F, at the point in n-dimensional space, x sub 1 plus h sub 1, x sub 2 plus h sub 2, x sub n plus h sub n, all that, the value of the function, when you've gone, h1 away from x1, h2 away from x2, hn away from xn, and they're not necessarily equal, we'll say they're not equal, the value of this function, capital F of x sub 1 plus h sub 1, where h1 is a constant, the value of the function, capital F of x sub 1 plus h sub 1, x sub 2 plus h sub 2, comma, x sub n plus h sub n is equal to the exponentiation in regard to the number e, which is given by, the number e is given by e equals 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, I guess we get the picture, plus ... this goes on forever. If we're looking at this, you guys, if you take that e, and you were to say, okay, let's take the number e and put this and exponentiate it to this power, so to speak. It's kind of weird. These are real numbers, perhaps complex numbers too, but let's not go there. Real numbers are a special kind of complex. Real numbers are a special kind of complex number. Let's just deal with the real numbers right now. Here's a real number, and these are differential operators. And I said the differential operators, just like here, if I had, d dt, if I took d dt to the mth power, if I took dt to the mth power, I got d squared dt to the m. So I got this operation going on. It's not necessarily a number, you guys. It's the operator itself is being exponentiated. Well, the way that plays out is, to actually get this on something like this, you'd be looking at it. You got something like this, you'd be putting that right there. Let me, I don't want to erase any of it, but let me go right here, guys. E to that means, e to that means 1 plus, let's see exactly how they actually want to play that when they play this stuff out here, guys. When they actually do it, I think they just have the 1 there, and then it becomes. Okay, for some reason I just want to be careful here, guys. I don't want to say something
That's not going to be the case, but it should be. I think what my guess is correct, but I don't. It's been one of those days. I'm not really trusting it. I think the one stays and the other ones are different, but let me just be careful here, guys, when we actually do this. I'm very confident it's the case, but don't want to lead you astray. It's definitely in here in the notes that I've tabulated from the past. Right. Okay, that's what I thought. Okay, just to be safe, though, guys, I didn't want to go there. But yeah, that's what we're talking about. So you're essentially, when you're doing this thing right here, it comes out to this E to the H1 D1 H2 D2 plus dot plus HN DN. Indeed, comes out to 1 plus, and then it's doing this, the H1D1 plus dot. Let's save a little bit of room here, guys. To the 1 power over 1 factorial. Plus the same thing here. This, it really, the multinomial theorem, notice what's going on here. Remember what we said here, there were n terms. Here, there were n squared terms. To here, there were n to the m terms. This right here to the 1 power is indeed n terms. This thing squared is n squared terms. This right here, H1D1 plus dot plus HN to the m over m factorial. This is indeed n to the m terms plus dot going on forever. So it obeys the multinomial theorem, and there is the factorial notation occurring underneath, and that's consistent with Taylor's formula. So fortuitously, in a sense, the exponential function has the n factorial in the bottom, the m factorial, the k factorial, whatever factorial it is, it's in the bottom. So fortuitously, through use of the multinomial theorem and the fact that the exponential function behaves according to the multinomial theorem, with all of these, behaves according to the multinomial theorem with all of these, and has the factorial notation, the factorials in the bottom, just like Taylor's formula has for a single variable. When you're doing all the mathematics, it all fortuitously comes out to give you this. This shorthand is very convenient, and gentlemen, I think it was Harvell and Pipes, you'll see it when we actually print it out, are the gentlemen who had Pipes and Harvell, 1970, had kind of given this notation. I'm sure they've gotten it from other places as well. But this this kind of follows from that. And I show how you can actually do that by using the chain, by how you can actually derive all this by first of all parameterizing all the variables. And you parameterize all the variables as a function of t. Each one of those variables is a function of t. So the whole function becomes a function of t. The whole multivariable function becomes a function of t if each one of the variables is a function of t. And then when you're doing derivatives and stuff, you're doing an elaborate and hopefully very patient process of the chain rule. And the chain rule here, n terms. Chain rule here, n squared terms. Chain rule here, n to the m number of terms. The number of terms is bigger and bigger. And the differential operators behave in the exact same way as though they were variables. And that's what gets you there. And you're going to have this. I'm going to have this printed out, and you can kind of just page through it. It lends itself a lot better to the argument when we go that way. Even try to give you a look at an error estimate there, looking at a remainder, how it goes. But this is essentially a pretty beautiful argument that the mathematicians give us in how this stuff plays out. And like I said, you'll have it right at the end of the video. You'll have a display where it's just going to page through under the title of you see the first page. It'll be Taylor's formula expanded for n variables. Okay? All right. Pretty fascinating stuff. It lends itself a lot better if you look at it, guys. Otherwise, it's literally about a 10-hour discussion. Unfortunately, time's not there for that. But it's all written for you. It's already there for you on Canvas. So if you look at the stuff on Taylor's formula, all of the discussion is there on Canvas, fully derived, fully discussed. And it's also, we're try to put accessibility as a link in the film as well, so you can look at it as well. It might be pretty convenient that way as well. All right, thank you, and we will talk. Take care. Bye now.